Hi, I'm Claire, and today I will be presenting on the AFL white papers, which is essentially an overview of AFL, the fuzzer. Before we get into anything, a fun fact is that AFL actually stands for American Fuzzy Lop, which is a breed of rabbit, so you'll be seeing a lot of rabbit pictures on these slides today. So before I get started on the technical details of AFL, I want to ask a quick question to my audience. So how many of you have ever written a unit test for your code? I imagine a lot of us. And now let me ask another question. How many of you are confident that your unit test caught every single possible weird input or edge case? I'm imagining not a lot of us. This is a question that's plagued most developers and anyone who writes code, and is exactly the problem fuzzing and AFL aims to solve. So, what is fuzzing? Fuzzing is any sort of automated software crash testing, and it's done by feeding in fuzz, which is some sort of random or unexpected or partially valid input. For example, if you're trying to test a vending machine, normal testing would be putting in $1 and pressing A2, while fuzzing is the equivalent of trying to feed in a bag of foreign coins and some Monopoly money as quickly as possible and seeing if the machine will explode. And so the goal is really simple, to find an input that causes the program to crash or freeze or behave unexpectedly. And as you can see in this graphic over to the right, all of these inputs are kind of unexpected. They're not what you would normally consider the usual input, and that's what fuzzing tries to test. So why was AFL created? What was the problem that it was trying to solve? So before AFL, we had two main ways to find bugs, but both had flaws. So the first method is blind random mutation, where the fuzzer will take an invalid file, randomly mutate it a bit, then feed it to the program. The issue here is that it almost never makes it through input validation checks. So it never really hits the deep code that actually performs the complex program logic, which is where the bugs really hide. So it's fast, but it's not very smart. Now, the second method we had was symbolic execution. So rather than guessing, it uses mathematics to analyze the code, calculating exactly what input will reach the program's inner logic. However, it's very, very slow, and trying to solve a complex program mathematically takes a massive amount of time and also a lot of resources, making it very, very expensive to use on real-world software. So how do we solve this? So imagine you're trying to find a hidden object in a room, but you're blindfolded. And so you are the fuzzer, and the hidden object is the bug that you're trying to find. So blind mutation is wandering the room randomly until you run into it, while symbolic execution is trying to draw a complex mathematical map of the room based on your footsteps. So rather than relying on complex math or blind luck, AFL relies on a simple feedback loop. So AFL's approach is like asking someone to stand in the corner and say, getting warmer or getting colder. And it does this by injecting code, tracking code into the target program, which allows the program to monitor its own execution paths. So this tracking code creates a cycle where the program is fed in a mutated file. Then it will report back with a feedback loop with information about what happened during that run, and it will note whether new code that the program hadn't run before was triggered. So here's the binary or the actual, target executable where the tracking code will be injected. Here are the possible results of execution. So everything went okay. It takes that information back to the buzzer. It says everything went okay, or if there was a crash or a timeout, it will additionally report that back, and the fuzzer will continue to generate inputs with mutations. So if the report comes back positive, aka something happened that wasn't expected, AFL will save that file, make it a new parent, and then start mutating it for the next iteration, acting kind of like natural selection. And so by favoring loops that increase code coverage, AFL is able to bypass validation logic organically without having to kind of rely on external resources, creating a hybrid approach that mitigates the weaknesses of the previous methods we mentioned. So what are AFL's design goals? The first design goal is speed. So the more executions you can run per second, the higher your chances of finding a crash. If a fuzzer is 10 times smarter but runs 100 times slower, the trade-off really isn't worth it for the user. AFL uses optimization tricks like the fork server to prioritize raw speed, which we'll get more into later. The second design goal of AFL is reliability. So programs can do a lot of weird things, as we all know, like entering infinite loops or tar pits, which are paths that take forever to execute without improving code coverage. So to mitigate this, AFL policies execution heavily and sets aggressive timeouts, assuming that there is a cheaper and faster way to reach that same code later. The third design goal of AFL is simplicity. So smart analysis tools break down when software gets really large or complicated, and so AFL relies on a set of simple test attacks, staying very lightweight and easy to use, which also helps it be more reliable. And the final design goal is chainability. So AFL is designed to be part of a larger toolkit, and it's not designed to be all encompassing or comprehensive. Its end product is a folder of unique files that trigger different parts of a program, so a folder of quote unquote interesting seeds. You can chain AFL very easily with other tools, like feeding its output into a symbolic execution tool to do the heavy lifting, or running it in parallel with other instances of AFL and having them automatically communicate with each other. So let's get into the more technical details of AFL and really how it works. So AFL's first secret is how it tracks code. So most old fuzzers only checked if a specific block of code was hit, essentially the destination, so these nodes here. And while this was effective, AFL does something better by tracking the journey or the edges between the blocks. So why does this really matter? Because in software vulnerabilities, the order of operations is essential. So reaching code block A, then B, then C is completely different than reaching A, then C, then B. So AFL will assign a unique ID to every single transition or edge. And it tracks all this by using a very small 64 kilobyte memory map, which is kind of like a scoreboard with a lot of slots to hold these edges. And so every time a program moves from one block to another, AFL will use a very, very simple math trick, essentially an XOR and a bit shift operation to calculate exactly which slot on the memory map or the scoreboard to tick. So it takes a random ID from the block that you're in, adds it together with the block you just left, and then claims a spot in the memory map without slowing the program down. So one question you may ask is, how exactly does this XOR math trick work? This is a great question. So the problem with standard XOR math is that A XORed with B is the same as B XORed with A, which kind of removes the whole point of us tracking the order of edges. And so if AFL used just that, we wouldn't be able to know like the directionality between these nodes. So to solve this, AFL uses a bit shift operator. And so it takes the current block ID, shifts its binary bits to the right, and then XORs it, preserving the directionality so that A to B is completely different from B to A in the memory map. And I thought this was a really cool technical trick that AFL utilizes. So moving on into the algorithm of AFL, specifically the evolutionary algorithm. What's interesting is that older genetic fuzzers used a greedy approach where they maintain a single test case and continuously evolve that test case. In contrast, AFL isn't greedy, and it saves every single mutated file that produces a new state transition, so those different edges that we talked about earlier. And in doing so, it's able to explore disjoint features of a data format at the same time. And so you can see here at the level 1 test cases that it's saving every single quote-unquote interesting edge. And so AFL relies on smart mutations rather than guessing randomly. So it'll use things like deterministic bit flips, different forms of math, as well as splicing different files or test cases together. And to determine which test cases survive, or the fitness test, only mutations that trigger a new edge on the scoreboard survive. So if it hits the same path as its parent, it's discarded, allowing us to discard, a lot of these initially interesting test cases and kind of narrowing down our search space. So this generates a synthetic quote-unquote corpus, which is a compact collection of files that basically say, hey, this does something new. So this algorithm and this approach has been found to be very, very effective. Testing on an application called GNU Patch, AFL found more than double the code blocks compared to other standard tools, and was actually the only method that found a unique crash. So looking at this mutation tree for gzip, on the left is our initial seed file in the green, and so it then fans out into this column of level 1 mutations. If AFL were greedy, it would pick the single best path here and then throw the entire, rest of test cases away. But because it's non-greedy, it keeps all these discoveries. Although admittedly many hit a dead end, but on the far right you can see a shallow discovery that successfully evolved all the way to level 6, reaching very, very deep logic, which is something that older greedy genetic fuzzers weren't able to do as effectively because they threw the initial level 1 test cases away. So moving on into how AFL actually mutates its test cases. So AFL follows a two-part progression. It starts out with very deterministic calculated steps, such as flipping bits or inserting known buggy numbers like 0 or the maximum 32-bit integer. This produces very small, very compact, and easy to interpret crashes. And once that's out of the way, it moves on to non-deterministic methods, such as splicing different test cases together or applying stacked mutations. During these early steps, AFL will build an effector map, which is essentially tracking whether flipping bits in a certain region does nothing to the execution path. If that's the case, then it'll mark that as dead space and stop fuzzing it, which helps speed up fuzzing significantly, especially in formats like tar archives, where they're block aligned, meaning that they have to pad their data out to specific, very uniform block sizes. I believe traditionally 512-byte block sizes using chunks of lots of zeros, so it's very sparse. And so they contain a lot of raw file data that the parser doesn't actually really care about or need to make any structural decisions about. So finally, AFL uses dictionaries to solve highly structured files. So using its feedback loop, AFL can automatically determine syntax tokens. By combining these tokens and then watching how the scoreboard evolves, AFL is able to organically reconstruct complex languages like JavaScript, SQL, or XML without relying on any external resources. So moving on to crash management and also crash exploration. So if a fuzzer runs millions of times, it will output maybe thousands of crashes. So how do you know which ones are unique? Older tools tended to group crashes by their memory addresses, which turned out to be very inaccurate. So AFL approaches this by considering a crash unique only if its execution path includes a new edge on the scoreboard, so filtering out the rest. In terms of exploring crashes, once a unique crash is found, how do we know that it's actually exploitable? So AFL has a crash exploration mode where it will fuzz the crashing file but reverse its own rules, and so it will throw away any mutation that doesn't crash, generating a bunch of inputs that trigger the fault and makes it a lot easier for a human to review. Finally, when AFL finds a crash, it turns its automatic file trimmer off. So it'll save the input exactly as it was discovered so that someone can put it side by side with the non-crashing parent and then run a simple comparison between the two files and then see the exact mutation that caused the crash. So moving on to trimming and the fork server. So starting a target program from scratch thousands of times a second is very, very slow due to the overhead from the operating system. And so AFL bypasses this by using a fork server. So it'll boot the program once, pause it, and then use a copy on write mechanism to clone that pause state for every new test, giving it a lot of performance gain. So for advanced users, there are two different modes. So deferred mode skips heavy initialization code, and the user has to manually select this, while persistent mode can try multiple inputs inside a single running process without cloning at all, so this also boosts speed. Finally, AFL also optimizes the files themselves. Over time, mutations cause these files to become very large and bloated, so AFL's trimmer will routinely delete random chunks, and if the smaller file hits the same exact path on the scoreboard, so the smaller file is covering the same edges, then AFL will permanently save the smaller version because they process faster. So that helps with its processing speed. Finally, touching on parallelization and black box testing. So to scale, AFL actually supports native parallelization. So you can run independent instances across multiple cores or different remote machines. They periodically check in each other's queues and then pull in files that trigger new behaviors locally. And so this allows for them to skip running those same files again when we already have the results remotely. So in terms of black box testing, if you don't have the source code to track or to inject the tracking code, AFL is able to use a custom version of the QEMU emulator where it will watch the compiled blocks run and then track the edges on the outside. And so you can even fuzz cross-architecture code like testing an ARM binary on an x86 laptop, which is really, really cool. So finally, generally, running emulators is usually pretty slow, but AFL is able to use a modified fork server and caches block translations. So because it uses, some of these optimization hacks, AFL's emulator mode only suffers about a 2 times to a 5 times speed penalty compared to maybe around 100 times slowdown in older tools. And this is kind of a snapshot of what AFL actually looks like. So you can see the map coverage and the count coverage, as well as different paths, where different edges are happening, different crashes, things like, what was the last new path, how long this process has been running for, things like that, which is pretty cool. Oh, and also the fuzzing strategies we mentioned earlier. The bit flips, the byte flips, the known integers, dictionary, etc. So let's move on to the limitations of AFL. So where does AFL struggle? As cool as it is, it's not perfect, right? The first wall AFL tends to hit is what we call magic values. So if a program has a very simple security check, like if input equals secret key, AFL is essentially just a really fast bit flipper, right? So the mathematical odds of it randomly mutating a file to spell that exact secret key is basically 0, so it'll get stuck. The second issue is the map collision problem. So AFL relies on a 64 kilobyte memory map, but for most programs that's enough, but if you fuzz a larger application like, I don't know, Google Chrome per se, eventually 2 complete different execution paths will collide by calculating to the same spot in that memory map. So this will cause it to overwrite its own data and then miss out on discovering new code. Third, AFL is structure blind. So if you're testing a program that expects a very, very structured format like a JSON document, randomly flipping bits will destroy this grammar. So changing the word name to NAMZ causes a basic syntax error, and the program will immediately reject it, meaning AFL wastes a lot of CPU cycles just generating bad grammar. Finally, AFL suffers from wasted time because it treats all of its interesting files equally. So it'll spend roughly the same amount of time mutating each saved file, but in reality, some files will trigger very, very rare, deep code, while other ones just trigger boring common errors. So by not prioritizing these rare paths, it can waste time. So what are some improved versions of AFL, or the more modern versions of AFL? So obviously we have AFL++, where the security community took AFL's open source foundation and then built massive improvements. So to solve the magic value problem, modern fuzzers, including AFL++, use hybrid fuzzing. So when a fuzzer gets stuck on a password check, it will pause, use some math to solve that one string, and then inject the answer, and then go back to the fast version of fuzzing, which is, a little dumber. To fix the collision problem, modern versions use dynamic and expandable memory or collision-free tracking, which allows them to test very, very large software without, having those collision issues. And to fix the grammar issue, we also have grammar-aware fuzzing. which we implemented in our capstone project. You can literally feed the fuzzer the dictionary rules of a language like JSON or SQL, and then instead of flipping a single byte, it'll mutate logical chunks. And that makes sure the output is always valid and testing the logic of the program rather than just the syntax parser or the validation checks. Finally, modern fuzzers use smart power schedules, where they use complex algorithms to figure out which paths are the rarest and the most difficult to reach, and actively prioritize spending more CPU time mutating those specific files. Let's wrap this up with some conclusions and some takeaways about AFL. So, here are some actionable takeaways. First, if you're writing software, especially in languages like C or C++, human written tests, unit tests just aren't enough. So I urge you to integrate a fuzzer into your testing pipeline and let the machine throw fuzz at your code before you ship it. And you may ask, does AFL only work on code written in C and C++? So out of the box, classic AFL was primarily designed for C, C++, and Objective-C because it injects the tracking code I mentioned earlier during the compiler stage using things like Clang or GCC. However, as I mentioned in the black box slide, you can use the QEMU mode to fuzz any compiled binary, but it works best on memory unsafe languages. However, more modern versions like afl++ have added support for languages like Python, Rust, Go, and probably more. So the second takeaway is to match the fuzzer to the target. There is no catch-all solution, and so you have to match your security and fuzzing tool to your target. If you're testing an image viewer, classic AFL is probably a pretty good tool. If you're testing a database, you should probably use a grammar-aware fuzzer so you don't waste a bunch of time on syntax errors. And the third and final takeaway is to prioritize speed over elegance. Perfect is often the enemy of good. Don't get bogged down waiting for mathematically perfect, very elegant, comprehensive analysis. As AFL proved pretty historically and in a groundbreaking way, a fast, reliable set of hacks that run millions of times will often find a lot more real-world bugs than a really elegant theory that takes, a lot of resources and a lot of time to compute. That's all I have prepared today. Thank you for your time, and hopefully this was a pretty interesting presentation that you walked away learning something new from.